Okay, so good day, everybody, and welcome back to our webinar series. And we're lucky today to have Ronnie Mckenzie, who's going to be doing our first webinar. And he's going to be giving us a webinar today on the interpretation of minimum night lines. And I think it's going to be a very interesting webinar. I can see we've got a lot of people online already, which is very good. So you're all obviously all raring to go again. So I shall hand it over to Ronnie. Ronnie, please go ahead with your webinar.
Hey, good morning, everyone. As you know, my name's Ronnie Mckenzie. I'll be presenting the webinar today, which will give you some practical tips on monitoring and interpreting minimum night flows. Before kicking off, I'd just like to thank Stuart Hamilton, the chair of the IWA Water Loss Specialist Group, and Gary Wyeth, who's the secretary, for setting up these webinars. From my own experience, I know how difficult it is and time consuming to do these things. And I know that generally it's the secretary that does all the heavy lifting. So Gary, thank you for all your hard work there. And thanks again to Stuart for the initiative, which I think is wonderful. Today, we'll be looking at night flows, or night lines, as Gary called them. And I'm just going to take you through the sort of general principles and give you some tips on our experience here in South Africa on how we've used minimum night flows and what we do with them and how you interpret the results. So we kick off basically with a slide, which is a 3-day flow logging result into a discrete residential zone with no pressure management. And the question I ask you all is to have a look at this graph and tell me whether you think we have a leakage problem. Okay, now with this being a webinar, it's a bit of a rhetorical question, that one. However, just have a look at it, make up your mind whether we've got a leakage problem. Do we have a leakage problem or not? And we'll come back to it at the end of the presentation. And hopefully by then, you will may change your mind. Maybe you were spot on the first time. Now, I'm going to just give some background to understanding leakage, touching on what the IWA is doing, as well as what the BABE methodology has helped around the world in doing. When we talk of leakage, and I'm speaking from we work most of our time in developing countries. So we have burst leakage, which is the large leaks. We have background leakage, which is the sum of all the small leakage. And in many of our cases, we've also got a problem with internal plumbing leakage. Normally, that wouldn't be a problem to the water utility if the residents are paying for water. But in countries where you've got low levels of payment or even free basic water, the internal plumbing leakage can be quite significant, in which case it does become a problem of the water utility. If people are not paying for the water, your internal plumbing leakage can sometimes be sky high. Now, we use the BABE methodology quite a lot. You'll have heard of that. BABE methodology is, it was originally developed by Alan Lambert and some of his colleagues at the UK water industry. It was a simple, relatively simple and pragmatic approach to managing physical leakage in water utilities. And the technology and the methodology has since been presented around the world and adopted by a great many countries. South Africa was probably one of the first countries outside of the UK to embrace the BABE methodology. And it basically splits leakage into two components: burst leakage, which is your large leaks, and background leakage, which is the sum of all the small leaks. Now, the definition, the original definition, it may have changed a little bit over the years, was that if a leak is above 250 litres an hour, it would be classified as a burst. And if it's below 250 litres an hour, it would be classified as background leakage. Background leakage, you cannot get rid of. It will always be in your system somewhere. Burst leakage, it's cost effective to go looking for it and to repair it and fix it up. So depending on what blend of leakage you've got in your system will determine what interventions you will use to address it. And that's basically what we're looking at. This is just a picture of a background leak. It's a tiny little leak. It runs all the time, doesn't really cause any damage. You would probably not be able to pick it up with leak detection equipment. Even if you could, it would probably not be cost effective to do so. Burst leakage, you've got mains bursts and connection bursts. A mains burst, this is a picture of a mains burst here. This is running at about 20 cubic meters per hour. A typical mains leak will run at anything possibly from about a cubic meter per hour, on average up to 10 or 20, but it can go as high. We've had mains bursts up to 1,000. So it can basically be, it depends how big your pipes are. There's a connection burst. This is also a burst, but it's on the connection pipe and not the main. It would normally run at anything from about half a cubic meter per hour up to about 1.5 cubic meters per hour, depending upon the pressure and how bad a burst it is. These leaks tend not to receive the attention they deserve, and we'll touch on that in a little bit. Now, the burst and background methodology was originally developed, as I mentioned, by a group of specialists from the UK water industry. They put their heads together and came up with various approaches, and they had 4 main components to addressing physical leakage in a water utility. One of them is the logging and analysis of minimum night flows. Another is water auditing and benchmarking of leakage. Third one would be the economics of active leakage control. Sometimes it's termed economic level of leakage, but in my experience, we're looking specifically at how often to send a team in to carry out active leakage control, which means to look for leaks which have not been reported. So we consider it the economics of active leakage control. And finally, pressure management, which is one of the key elements in addressing leakage. Today, I'm going to concentrate mainly on the logging and analysis of minimum night flows. So I'm not really going to look at the others. I'm sure they've been covered in various other webinars. But in South Africa, back in the early 1990s, Alan came over to South Africa and we developed our 4 models through the Water Research Commission. This slide's been replaced by a more politically correct slide. So we use this slide now for our 4 BABE models. And we have the 4 programs. We've got sand flow, which is a night flow analysis model. We've got the bench leak, which is a water auditing and performance indicator model. PressMac is your pressure management model, and EconoLeak is the economics of active leakage control. Now, these are models that we developed together with the UK specialists, and they are provided free of charge here in South Africa. There's a huge range of these models now. They've been updated and improved, and various countries around the world have versions in different languages. etc., etc. So if you want to know more about any of the components of BABE, Bursting Background Estimate methodology, there's huge information on the internet. You can download the software freely. You can get the information. So we've got our own versions here in South Africa. We use them sometimes. The manuals are quite helpful to people wanting to get into the industry. So there's a huge number of models and manuals and papers written about this. So I'm not going to go into much detail. On our sand flow model, I'm not even going to really talk much about sand flow. Basically, the sand flow model is the one that I like best, probably. It covers the principles of the bursting background estimates. It helps you to analyze what is below your minimum night flow. How much of the water going into an area at night time would you expect to be there, and how much is unexpected leakage, which is then an indication of whether you've got a burst problem or not. So again, I'm not going to go into the detail of this. It's all in the manuals. It's all been covered many times before. But what's quite interesting, here's a 3-day logging result. The flow, as you can see, is in blue, and the pressure, the corresponding pressure, is in red. Now, this is the flow and pressure recorded at a water meter going into a zone. There is no pressure management here. The zone is discrete. It's a residential zone. Okay. Now, what you see there quite clearly is at night time, generally from about 10 o'clock at night till about 6 o'clock in the morning, the pressure in the system builds up, mainly because the consumers are not using much water. And that is when you get your period of minimum night flow. And it generally corresponds with the pressure being at its maximum. Okay, so the purple line here represents your minimum night flow. What we've then got is we've got an expected minimum night flow, which I've drawn here in a green line towards the bottom. Now, I've shown it as a straight line. It's not actually a straight line. Some of the components of your minimum night flow are, of course, pressure dependent, in which case you would have a bit of variation in your minimum night flow. But for today's webinar, just accept it's a straight line, okay, for purposes that we're talking about. The difference between your measured minimum night flow and your expected minimum night flow is then an indication of whether you have a leakage problem or not. So that purple area is your unexpected night flow. You're not quite sure what it's there for. It could be leakage. It might be caused by something else. But there's a strong possibility that it is leakage. And what we're trying to do is identify the zones that have the biggest problem and spend our time and effort fixing it. So here's another logging result. And this is a 7-day logging result. Do we have a leakage problem on this one? Well, if you look at the minimum night flow, it's 18 cubic meters per hour. This is the flow going into a residential area. I've not told you how big it is and how many houses, or it doesn't, I'm not really too worried about that. What we try and do is we normally draw a line on our graph which represents the average daily demand. Now, you can use a spreadsheet or a computer software to do this if you really want to take it to a third decimal, but you can also just eyeball it if you really want, and just try and get the area in grey above the line balancing with the yellow area below that line, and you won't be far out. I've said it's 64 cubic meters per hour. It might be 66, it might be 62, doesn't really matter. It's just a rough indicator. And what we do, and again, this is something we've been doing for years, It's not in the textbooks as such, but it works for us, and it may work for you. It might not. You might have other things that you do. What we do is we come up with a night flow ratio for each zone, and this changes from week to week. And we use the night flow ratio as one indicator. There are others, but we use this as one indicator to tell us whether we think we have a problem in that zone. And I've used a ratio here. It's in this one, it's 0.28. Generally, in a developing country, leakage is quite high in most zones. And 0.28 in a developing country would be probably a zone that you would leave alone. You've probably got bigger problems to deal with somewhere else. In the UK and Australia, maybe even America and parts of Europe, that ratio would perhaps be considered very high, in which case you would maybe spend money going in and fixing it. As I say, where the problems we've got are just so big that if we see a zone like this, we're generally quite happy. We normally have zones that look like this. There you've got a minimum night flow of 125, an average daily flow of 150. Your ratio in this case is 0.83. And that's pretty serious. I mean, when you're up at those sorts of levels, generally, we find it's due to internal plumbing leakage that is just ballistic. It's just gone wild. And that is quite a serious problem for us. So in a logging result like this, you don't really need to be a rocket scientist to pick up that you've got a major problem. We do use other indicators. We use percentage losses, I have to confess, mainly because the politicians insist on it and they are paying our bills most of the time. So we do that for the politicians. It's one of the indicators that they think they understand, even when we tell them it's potentially very unreliable. We use the ILI, which we tell them is very good and it's really reliable. They don't like that one because it's too complicated for them. They're just politicians, so they don't like those ones. We use liters per connection per day or all sorts of things. That gets really complicated. Most people. So anyway, you can use what you want. I'm just showing you what we use, and we can debate that at infinitum. Logging. When it comes to logging, we use different loggers. Everyone's got their own preference to loggers. There's hundreds of different logger makes out there in the market. We like loggers which do not require main supply. We like loggers that are battery powered, preferably that don't require solar panels to power them, and hopefully we'll have a battery that will last 6 or 7 years. Other clients like different loggers, electrically powered or mains powered loggers, battery powered loggers. There's all sorts on the market. If it works for you, great. Every country has different problems. Our main problem is theft, particularly of electrical cables. Anything involving an electrical cable is a liability in many countries where we work in Africa. This is one of our loggers that was out in the field at the Kruger Park for about 7 years. It ran out there in the sun, in the heat. The battery didn't explode. The logger worked well, lasted, as I say, 7 years. It would have lasted longer. It got washed away in a typhoon. I think it was a major cyclone. We don't get typhoons, we get cyclones here. There was a big cyclone came through. The river came up and wiped out everything. This one's even elephant proof. It managed to survive elephants and all sorts of things. This is another one that one of my colleagues, Brad, took a photo of when he was at the Kruger Park. This is it was a different logger. It did require solar panels. As I say, I personally don't like loggers that need solar panels because the solar panels will generally get stolen if you're anywhere near a residential area. In this particular case, it seemed to have its own protection squad in place, so it wasn't a problem. When it comes to meters, Again, every country has a different philosophy regarding meters. Just be careful when you're using loggers that if it's a combination meter, remember to log both meter heads and add them together. Sounds very basic, that, but you'll be surprised how often it doesn't happen. We protect the loggers because they will get stolen. It's got a battery in it. Anything with a battery is fair game. So we normally stick our loggers into metal boxes, which protect them. And we get signal through. We find the metal doesn't really stop our GPRS signal going through the logger. We use GPRS loggers. We also use Sigfox. We use LoRa. We use RF. There's no single silver bullet that fits every gun here. So we try and tie them all together into a common database and use the different, whatever the clients want to use, we use. Before going on to logging results and leakage and all sorts of interesting things, I just want to touch on another issue. How much water do we lose through a leak? Now, we've got a few examples here. I've shown you this one already. This is a mains leak running at 20 cubic meters per hour at a pressure of about 50 to 60 meters. And you wonder how much water you're going to lose through this. Well, the answer was 60 cubic meters. This leak from starting ran for approximately 3 hours. And after 3 hours, the water was shut off, the leak was fixed, and the total water loss through that leak was 60 cubes. This is another one. It's a slightly bigger one. It's also a mains leak, obviously. This particular one was running at 40 cubes per hour. And you can see there, this one ran for about 6 hours. And during that time, it lost 240 cubic meters of water. So it's a bit more than the previous one I showed you. Here's a very large leak. This was it was about a 1 meter diameter high pressure water main running at about 300 meters of pressure. One of the welds on the pipeline gave way, and you can see the water there going up to about 70 meters in height above the trees there, and you can see houses in the background. This is an absolutely enormous leak. It managed to get into the newspapers and probably the TV crews would have been there. However, having said that, it was fixed again within 3 hours. And it was, although it looks very big, it was running at about 200 cubic meters per hour. It wasn't actually, it looks a lot more. This leak lost about 600 cubes of water. So not as much as you might think for something that takes up half the landscape there. Here's our small one again. This is our little connection leak out in a residential area. This leak ran for 3 months, which was quite important if you think about it. It was running at about a cubic meter per hour. It looks a bit more, but it was a cubic meter per hour, this particular one. It ran for 3 months and it ran up a total loss of about 2,200 cubes of water. So quite significant, small leak, a lot of water loss, even much more than the one I just showed you that was 70 meters high. And last of the leaky pictures. This is a stormwater drain at the side of a road. If you look in the small picture on the left there, you can just see this is a stormwater, this is a road. You can just see the water there in a bit of a damp patch. It wasn't really causing a lot of problems. When you looked inside, the water was gushing through from a pipe at the back of the stormwater drain, which had obviously burst, and it was running into the storm water. It hadn't caused any damage, and it really wasn't bothering anyone. And the pressure going into the local houses wasn't really affected that much. As a result, this leak ran for over 3 years, and it ran up a total loss of 13,000 cubes per hour. So what the message here is, it's not always the size of the leak that will dictate how much water you lose. It's how long you take to fix it. And it's very important to fix even small leaks, especially if they've been reported. So just one of the takeaway points when it comes to water utilities, you should be fixing all reported leaks within a day or a maximum of 2 days. Unfortunately, most of the municipalities we work for, that repair time is generally in a matter of weeks, if not months. And that means that we're losing a lot of water, particularly through the smaller reported leaks. Okay, technology, finding leakage. I'm not going to go into all the different, you'll have had lots of presentations by people telling you about all sorts of fancy ways of finding leakage. I'm just touching on a couple of them, which I found quite amusing and interesting. Let's see. Satellites. There's lots of companies offering to find leaks with satellites now. I believe they're going to push up hundreds, if not thousands, of new satellites over the next 5 or 10 years, which means that satellite technology will become cheaper, and it may well be viable to find leaks using satellites. I have no doubt that they're successful. I think it's development, it's going to happen. Is it worth it though? That's the question. We've also got low tech solutions. I noticed there was a nice one. The UK, one of the UK water companies was showing pictures of a dog that they've trained to look for leaks, a large canine leak detector, an LCLD is the acronym for that one. I don't know how many of them there are and how well they work and whether they're in a union or not. But anyway, they've been trained to pick up chlorine in the water, which I believe can work. A lot of our leaks go through the soil, and by the time it surfaces, we don't pick up a lot of chlorine. I don't know if that might be a problem or not. But anyway, I think it's a good idea. I like dogs. We tried it here in South Africa. We had an international team of dogs. We had a Rhodesian Ridgeback and an Italian Greyhound. And there they are. That's our leak detection team. We tried a different technique, but it wasn't overly successful. I think that's probably the right way to term it. They did find a couple of bones and the odd toy, but other than that, we gave up on the dogs. Joking aside, a lot of areas that we work in, the leaks are just obvious. You don't need a satellite or a dog or anything apart from your eyes to spot the leaks. And if you have leakage like this or this, then you really don't want to be wasting money looking for new leaks if you're not already fixing the ones that you know about. So one of my takeaway points today is before you implement active leakage control, the most important thing is to fix the reported leaks that you already know about. If you're not doing that, I don't know how much point there is looking for new ones. Are you just going to make a list of all your leaks and not do anything about it? So rather use the money, fix the ones you know about. Once you've got them under control, by all means, go looking for new ones. Okay, using data acquisition systems to reduce leakage. Data has become very cheap over the last 10 or 12 years. Equipment has reduced in price, looking for monitoring things. You can monitor huge amounts of information nowadays: pressures, flows, TDS, chlorine, borehole levels, rainfall, anything you want, you can basically monitor. And it is becoming cost effective to do it on a continuous basis in many cases. Not always, but certainly in many cases. We've got our own system where we use loggers and we bring them into a centralized database. I think we've got about 12,000 reporting daily between industries, townhouses, all sorts of things like that. We can also use LoRa, Sigfox. I don't know if you've got Sigfox coverage where you are. We've got complete Sigfox coverage everywhere, which is quite convenient and also very cost effective. So you've got different mechanisms for grabbing the information. We pull it into a centralized database that can use anything. And we then look at the results and we send out reports or alarms, or we write up reports or send out strategies to people based on what we find. I'm going to show you a few logging results now for the last part of today's presentation. And we start with an office complex. These are all real examples. They're all taken out of our database. This is an office complex, small office complex, 5 offices, each with about 30 people working in the office. And we started continuous monitoring about 3 years ago. When we started it, we were not aware that we had any problems at all at the time. I'll come back onto that. This is a 4-week logging result of what you would want to see. And you can see that we've got 5 days where people work, and then we knock off for the Saturday and Sunday. So that's quite nice. You might not always do that. You might have a Saturday and Friday and Saturday off, for instance. You can see that we pick up holidays quite easily. If there's a holiday, most people are not in at the office. So the weekends are generally very low and the weekdays are quite high. You can see that we've got a virtually zero night flow at over the weekend, which is what we're looking for. So we do not have a leakage problem from this 4-week logging result. However, another 4 weeks, we move on 4 weeks. 4 weeks down the road, we now have a different situation. You can see we had a holiday there. That was the 1st of May. That's May Day holiday. Then you had Wednesday, Thursday, Friday was your normal. Then you had the weekend. Then the following week, we put in some low flow toilets, some dual flush toilets, in order to try and save water. They were expensive. It's a European brand. We didn't put in cheap equipment. And we find that they don't seem to work that well with the water quality that we have. They the valve keeps sticking because we've got bits of grit and silt sometimes in the water. So we've had trouble with the dual flush toilets, not because they weren't good quality or properly made. It's just a combination of the poor quality in the water and the fact that we're not filtering the water perhaps before putting them into the toilets. So that was a problem. Our water consumption went up instead of down when we put in our dual flush toilets. This is another example. This is a growing leak. And you can see here the leak is growing. And it starts there. There's the leak starting. And it grows. It gets repaired after about 4 weeks, 3 or 4 weeks. That wasn't we reported it to the body corporate. And the body corporate that manages this office estate, they then do we need to get 3 quotes and we need to call plumbers, and you get 3 quotes, and then do we go for the cheapest or do we go for the best? So you end up wasting 4 weeks and you run up a bill of 50,000 Rand just to save 2,000 Rand by having quotes from different plumbers. Anyway, I won't dwell on that. You can see our toilets are still leaking, but it's a nice example. You can see that quite clearly, the leaks growing. Sometimes leaks grow, sometimes they don't. We've had leaks in this office complex that have stayed virtually constant for 6 months or more. So it does happen. Here's an example here. You can see at the beginning, the first 3 weeks, there's a pretty constant leak there that wasn't growing. It was nice and stable. That's our initial leakage. We did go in and we found the first leak. It was a small one. Generally, it's normally more than one leak. We found the first one there and then the second one there. After we found the second one, we got back onto a normal 0 leakage office complex. What was quite interesting, once we managed to get down to a 0 night flow, what was quite interesting on this one, let's just move this over here a bit. What was quite interesting on this one was that the overall water consumption used by the office complex dropped by 80% from start to finish. That's quite significant. This is an industrial site. Again, you can see what's a leak starts there. There's your leakage. You can see that we've got the weekend and then 5 days. So you can see it's an industrial site, this particular one. The leak gets repaired. It took 10 days. And that leak was running, I think it cost about $2,000. It lost about $2,000 worth of water. Had we not had the monitoring system, it would probably have run for between 3 and 6 months, because although the water account gets sent out every month, they often only read the meters every 3 to 6 months. They don't always read them monthly. So that's quite an important issue. So continuous monitoring is almost an insurance policy against a huge water bill. Talking of which, this one ran for 3 years. This is an interesting leak. This was an industrial leak. It ran at 25 cubes an hour for 3 years. The water bill for that at current tariffs would have been between $1 and $3 million. So that was quite significant. There's a big one. That was a leak. That was a plastic pipe. It had probably been cut when it was put in the ground, and it ran for 3 years before it was picked up. The leak at 25 cubes an hour, you would normally expect it would cause damage and buildings would fall into a big hole or something. This one was actually it was running into the sewer. So the sewer, we had a sewer running at 25 cubes an hour for 3 years. Needless to say, there was never any problem with the blockage in the sewer. So that was a positive. Here's another one. This is quite a common one that we get. If you have an evaporative cooler, where you have a big pan of water and you've got a big fan blowing air over it in order to act as an air conditioning unit. In this most people don't know how much water these evaporative coolers are supposed to be using. And this particular management agent obviously felt that 54 cubes a day was a realistic number for an evaporative cooler. After we fixed the inlet, or it was a ball valve replacement, it dropped from 54 down to 18. So we reduced the water consumption here by about 60%. And even then, there's still quite a bit of leakage, as you can see towards the end. This is an 8-day logging result for an industrial commercial property. Now, this one you can see quite clearly has a leakage problem. You can see it's running at about 50 cubic meters per hour, not per day, per hour. And the pressure in red, you can see it's going up and down as pressure tends to do. During nighttime, it's high, and during the day, it's low. However, what's quite interesting here is that our pressure and flow are now working together. So normally you would expect a minimum night flow. In this particular case, we've got a minimum day flow, or MDF for short. So we have a minimum day flow. Don't quote me on that new acronym. That's just one I made up in the spur of the moment. Anyway, the minimum day flow was caused by enormous leakage. The consumption was virtually zero. The leakage was running at 52 cubes an hour. And the only reason it wasn't higher was because the supply pipe couldn't handle any more water. That was the maximum flow that could go into that area through the supply pipe at that system pressure. And it was reacting to pressure. That's why the flow during the day was actually lower than at night time because of the pressure. So it's quite a nice example, that one. I've got another one here. This is intermittent supply. Again, you can see we cut off. We don't want anyone to do intermittent supply. It's an absolute disaster, but it does happen, unfortunately. What's quite interesting, as soon as you open up the network after intermittent supply, you'll often get a refilling spike. If you're using mechanical meters, the refilling spike can seriously damage the bearings in your meter and burn out the meter effectively. So you've got to be quite careful here. What we did do in this case, we got the client to keep the water on for 48 hours just so that we could see what was happening and get an idea of your leakage. And again, in this case, the leakage was astronomical. It was up at about our ratio, our minimum night flow ratio was about 0.83, which is, I mean, you're talking of massive, massive leakage. That tends to happen when you use intermittent supply. So we don't recommend intermittent supply. This is a slightly more complicated one. Give you something, we'll keep the best to the end. There's only two more, so you can get a cup of tea in 5 minutes if you can hang in there. The red line at the top is your upstream pressure. So there's your upstream pressure up here, which is quite constant at about 130 meters. It was reduced using a pressure reducing valve down to about 80 meters, which is still pretty high actually, but anyway, it's better than 130. What you can see is you can spot that the minimum night flow is running roughly about 12 or 14 cubes per hour. Okay, there's your minimum night flow, 12 cubes per hour. Suddenly it drops down to 0. So the minimum night flow goes from 12 to 0. Now, that would normally be something you would be looking for. You'd want 0 minimum night flow, but not going into a residential area that you know has hundreds or thousands of houses. It means something else is happening. And the clue is these little blips here at midnight through till about 6 in the morning. You can see them there. There's 3 of them. 3 blips over 3 days. Your night flow is 0, and you've suddenly got excess pressure going through the pressure reducing valve, which is controlling the pressure into the area. What is happening here? Well, basically, what's happening in this particular case is that someone has opened a boundary valve and you're getting excess pressure feeding into your zone through quite a small pipe. During the daytime, when the demand is high, it really doesn't make a big difference. You don't notice it. There's not enough capacity in the pipe to pressurize the whole zone. But at night time, when the demand is low, that pressure from the external zone is enough to push the pressure in the zone higher than the downstream pressure of the pressure reducing valve. The pressure reducing valve then closes, and that's why you get a 0 minimum night flow. So this is a case of a boundary valve being opened. Okay, that's quite a nice example, that one. Here's another example over a period of 1, 2, 3, it's about 14 days, somewhere around there. You can see the pressure in red. It was controlled by a pressure reducing valve. So again, we've got pressure control going into the area. We're not using modulation of any sort. So it's just a bog standard PRV. This pressure was stable, running at about 40 meters of pressure for the first few days. And then it starts misbehaving for a period of a week, and then it just goes ballistic at the end. What's happening? Look at the minimum night flow. We start off at 40, and suddenly it's up to 60. So we've had a burst pipe, okay? There's your burst pipe there. It then gets repaired. So we repair the burst pipe. It was a mains burst. 20 cubes an hour is quite a big mains burst. We repaired the pipe. You can see the minimum night flow now drops back down, not quite to 40 where it was. So it's a bit higher. And then it starts creeping up every night. And you can see the minimum night flow here. There's the minimum night flow. It's creeping up every night over a period of about a week. The reason it's creeping up is the pressure reducing valve is gradually failing. Obviously, something happened when the pipe was repaired. Maybe a stone got into the valve and tore the diaphragm, and the diaphragm is gradually disintegrating over a period of about a week. Eventually, the diaphragm completely goes and the system moves on to no pressure control from the valve whatsoever. This is quite a nice example, clearly demonstrating that pressure drives leakage. So that's quite a nice example. And here we go. We're back to where we started. Do we have a leakage problem? And there we have a 3-day logging result. I don't know if any of you are going to change your mind from what you decided at the beginning, but anyway, there's your minimum night flow, 80, your average daily flow, 150. Our little ratio that we like to use, which is our preference, it's a free world, we can use what we want, is 0.53. Even in South Africa, that would be considered quite significant. We have a leakage problem. And the answer to the question is yes. And on that, I will stop there. Thank you for your time.
Thank you very much, Ronnie, for an entertaining presentation as usual. Now, if anybody has any questions for Ronnie on anything from the webinar or anything else, then please use the chat function, which is at the bottom of your screens, and then you can type your question in there. We've had one question already, Ronnie, who is from Michael, and Michael said, with society becoming more 24/7, at least pre-COVID, I would assume nighttime consumption is now higher than ever before. How would you take account of this, as surely genuine nighttime consumption can look like leakage on DMA flow graphs?
I think it depends where you are. I think it's horses for courses. I mean, if you look at certain cities around the world, some cities never sleep, in which case using a night flow to try and identify leakage is obviously going to be a problem. In most residential areas, most people do sleep at night sometime. And we normally do find that we get a minimum night flow sometime during the night. And it's simply, you need to judge each zone yourself and decide, have you got a zone full of party animals who simply party all night and then sleep during, maybe you've got a minimum day flow, maybe they sleep during the day. It does work. Minimum night flows do work in the majority of areas. And I think even in areas where more people are awake at night or working shifts, etc., I think you will still find that you get a minimum night flow. And it's maybe you'll find that that expected part of the minimum night flow might increase and you may change your parameters. That's where the Babe analysis is quite flexible, because it allows you to make estimates of what you think the legitimate night use is. in that particular zone. So you'll just tweak the parameters to your specific situation. And maybe instead of, I don't know, 3 people per 1,000 flushing a toilet at night time, you might have 50 people per 1,000 flushing the toilet in this party zone. It really, you'll still pick up the leakage. Generally, your expected minimum night flow will be relatively small compared to the leakage in a zone that has high leakage. You'll spot a zone with high leakage. I don't think it is an unsurmountable challenge.
Yeah. And what about over the last year with the COVID lockdowns and factories being forced to shut? Have you seen significant changes in the night lines or even diurnal patterns?
Not really.
Not really?
I would say not really. I mean, obviously our office complex, I mean, we've got some really interesting results from our office complex. We just have a flat line for 2 weeks. It's like they shut the whole country down. It was like a lockdown. You're not allowed to go into your office. We had a flat line, like 0 minimum night for 2 or 3 weeks. So, I mean, clearly it does impact on it. But I haven't seen a case where the minimum night flow has jumped up due to people being stuck at home and being forced to drink and party all night and flush toilets and have showers and party again. I don't know. I don't think anyone here's got money for that. I think they've probably got over it by now.
So we've got 2 more questions, one from Andrew and one from Stuart, and I think they're sort of similar in concept. Andrew's question is, the expected minimum night flow is estimated, and how do you estimate it? And Stuart says, what are your recommended approaches for developing allowable night consumption for residential and commercial flow rates?
Okay, I deliberately didn't go into that during this talk. I think I did show you one slide which broke down the minimum night flow into the different components. And basically, when you're analyzing the minimum night flow, you're trying to estimate what you would expect it to be. So you're looking for what legitimate night flow could be expected in a zone. And the 2 main components of that are legitimate night use by residents, which is flushing the toilet. It is using a tap to brush your teeth or having a shower. Basically the main consumption at night time is actually toilet flushing. So you make an estimate, out of 1,000 people, 6% are going to flush the toilet in any 1 hour. So you say it's a 10-litre toilet flush. So 60 people flushing 10 litres is 600 litres. That would be your expected toilet flush use during that hour. You then calculate the background leakage for the length of mains and the number of connections and the number of properties. And that's where the BABE methodology from the UK water industry have already provided estimates of what you can use for those estimates. Like you would maybe assume 20 litres per kilometre of mains per hour. You would maybe assume 3 litres per connection per hour before the meter and 1 litre per connection per hour after the meter. Those are all numbers that you can play about with, and you can test the sensitivity of your end result on those numbers. So I deliberately didn't dwell on the calculation of the minimum night flow. It's all documented in the manuals, and you could probably have a webinar just on that, where you discuss these different things. And Stuart's question about have we got estimates that we can use, etc., etc. I think there's quite good documentation from the UK water industry on what numbers you can use for these different components. I mean, it's a component-based analysis methodology. And I'm sure lots of new research has been done to give updated information. Every country is different. I mean, Bangkok will be totally different to Pretoria. I mean, Pretoria, you've got zero night flow after 9 o'clock. In Bangkok, it doesn't really, things don't kick off till about midnight. So you'll get different water balances for different cities around the world. So there's no one size fits all. You have to look at each city and each zone in its own merits and try and come up with what is a sensible approach. That's my view.
Okay, we've got an interesting question from Fata. He says, when customers have big ground tanks, even if the supply is continuous, the minimum night flow monitoring doesn't give a reliable result because one or other customer might be filling the tank. I am facing this problem in my current work area. Do you have any suggestions?
Well, that's a tricky one. It depends. A lot of these ground tanks, I mean, it depends whether you've got leakage in the tanks or not, because now if you're filling a ground tank, at some point, you would expect your tanks to be full. Like if you've got a holiday season or something like that, and you've had continuous pressurized supply, there would normally be periods when you can get a minimum night flow. I mean, we have the same. You can always find problems with the approach, but generally you can sometimes find a spot where it's a national holiday and no one's using water, or it's a very wet period where no one's irrigating. I mean, that's the other issue here. You know, if people irrigate at night, they put automatic irrigation systems on. How do you know the difference between that and a leak? So, you know, it's not straightforward, and I appreciate that is potentially a problem in the areas where you've got groundwater tanks. We typically don't have groundwater tanks in most of the areas that we work around Africa. I know that it's quite common in many parts of Asia, etc. I know particularly in Thailand, you've got a lot of groundwater tanks that get filled up. But there should be a period sometime in the year when these tanks would all be generally full and everyone's fasting or not using water. And you should be able to get a minimum night flow at some point. But maybe not. Maybe it's not going to work for you, in which case you have to do something else.
A question from Chris, which is software like Sandflow suitable for small communities of up to 3,000 customers or 3,000 water meters?
Oh yeah, 3,000 is a good number. Yeah, I would say so. For a zone, absolutely. Right. I would say once you go below 1,000, maybe Alan Lamberts might have he might have better ideas on this than me. I would, once it goes below 1,000, it tends to get a bit twitchy. You know, like just 1 or 2 leaks can really, you know, sort of mess up your whole calculation. But once you're up at 3,000, that's a decent sized area. That's a nice, are we talking 3,000 connections or 3,000 people?
3,000 connections.
Yeah, that's quite a decent, I mean, that's a decent size. That's a good zone. I mean, the BAPE methodology was designed for that size of zone, really. I mean, it's a standard residential zone. It's when you've got mixed areas where you've got things running 24 hours a day. You know, if you've got industry mixing in with residents, then it starts getting a bit tricky. You need to monitor the actual industries themselves that are 24 hours and take that off the night flow and take it into account as part of your legitimate night use. So, but it can be done.
Yeah. And that comes on, legitimate night use comes on to a comment from Syed, which is a percentage of meters in a DMA could be read in the night between 1 and 4 a.m. to find out the expected legitimate night consumptions. Of course, that's assuming that you have customer meters installed.
Okay, well, most of the areas we deal with do have customer meters, I must admit.
So you could do a legitimate night use calculation in those zones.
I mean, yeah, I mean, there's lots of research being done all the time by universities where they're going around trying to analyze what is legitimate night use. I mean, the UK water industry did huge amounts of research on this and came up with the figures that have been used, and other organizations over the years have been repeating it for their own country legitimate night use. So our experience is it's not that sensitive. If there's high leakage in an area, your expected minimum night flow is going to be a very small part of the night flow. And even if you make a mistake on your legitimate night use, it's not going to change the result that much. If you've got high leakage, you'll pick it up.
Yeah, okay. And we have one final question, unless anybody else puts one in, which is from Alice, which is, thanks for the practical experience. Have you ever worked with a ratio of daily input volume to the DMA versus the average authorized consumption per day?
The daily input, I mean, basically then that's almost like looking at liters per capita. That's almost working out the liters per capita per day, isn't it? I would think.
Well, it's almost like calculating non-revenue water, isn't it? Because you've got input volume and you've got your authorized consumption. So,
I mean, there's a number of different ratios that I think people can use if it works for them. I mean, we find the one I like, the night flow one. My view in life is if you've got your minimum night flow under control and it looks good and you don't have a high ratio, then you don't have a leakage problem. If your minimum night flow is out of bounds and it's high, then you know that something is going on in that zone that may or may not be legitimate use. And we use that regularly. It helps us enormously. And so I can't say that I've used the other ratio that has just been mentioned, but we do look at liters per capita per day and compare that between zones, and you find out. But again, a lot of that is to do with different levels of residential accommodation. You know, is it flats? Are people living in flats, or are they living in mansions with huge gardens and swimming pools? You start getting totally different pictures from some of the ratios. So I'm not saying our ratio is a silver bullet, but it works quite well for us to help us select zones which have a problem, and that's what we're looking for.
We got another question from Martin, which is, were you able to use the lockdown period to analyze minimum night flows in commercial or industrial areas that previously registered significant night consumption?
Yes.
Yeah.
Absolutely. It's been quite good for that. Some of the logging results are quite informative, especially if factories have been shut down. It's quite a good. This is a good time to pick up leakage. You don't want. What do they say? Never waste a good crisis.
Right. Okay. Okay. I think that's all of the questions that we've had. Ronnie's email is there on the screen, so I'm sure if anybody has any further questions, they can contact you, Ronnie, and with their questions.
Yeah, they're welcome. Yep.
Yeah.
No problem.
Okay. Well, thank you very much, Ronnie, and look forward to the next webinar, everybody, which will be next week. Thanks, Ronnie.
Okay, thanks very much. Bye, Gary. Thanks for your effort.